My name is Roshan and welcome to our project demonstration on implementing a neural network on FPGA for digit recognition using the MNIST dataset. In this video, we'll dwell into the fundamentals of neural networks, exploring the significance of the MNIST dataset and how we are leveraging FPGA technology to run these models efficiently. Neural networks. Neural networks are computational methods inspired by the structure and function of the human brain. At their core, neural networks consist of interconnected nodes organized into layers. These layers include an input layer, one or more hidden layers, and an output layer. Each connection between nodes is associated with a weight, which the network learns to adjust during the training. Activation functions introduce non-linearity into the network, allowing it to learn and represent more intricate relationships within the data. The MNIST dataset. The MNIST dataset is a collection of 28 x 28 grayscale images of handwritten digits, ranges from 0 to 9. It consists of 60,000 training images and 10,000 test images, making it a widely used benchmark for evaluating machine learning algorithms. Now let's look into the first module, which is neuron.view. This module is designed to represent a single neuron and encompasses key functionalities including memory handling, computation, and activation. The module efficiently manages the loading of weight values into memory, performs computations involving input weights and biases, and applies activation functions such as sigmoid or ReLU to generate the neuron's output. Now let's look into the input. This module has inputs such as clock, reset, my input valid, represent the input data to the neuron and indicate its validity. Weight valid and bias valid indicate whether the weight and bias data are valid. Weight value and bias value carry the weight and bias values to be loaded into the memory. Config layer num, config neuron num configure the neuron's position within the network, and we have the output signals such as out and out valid. The main operation performed by this module is memory management. When weight and bias data are valid, they are written into memory. Input data is read from memory based on the read address. The module does the computation such as MAC, bias addition, and activation function. Control signals such as the mem and R address facilitate memory read and write operation. Moving on to the next module, weight memory. The weight memory module is responsible for storing and retrieving weight data used by neurons in the neural network. It provides read and write access to the memory array, allowing weights to be loaded during initialization and retrieved during the network operation. This module has input signals such as clock, write enable, write address, read address, and the W in, W out. W in is the read in and W out is the wait out. The memory array is defined as a two-dimensional array of size, num, weight, rows, and data with columns. Each row represents a memory location storing a weight value with data with. The initialization is the pre-trained if-def block. If enabled, the weight memory module initializes the memory array with weight values read from a file specified by weight file. This allows for preloading weights trained offline into the FPGA. And then we perform the write and the read operations using this module. Moving on to the SIGROM. SIGROM module or the sigmoid ROM module is responsible for providing the sigmoid function values corresponding to input values received from other modules in the neural network. It uses a memory array to store pre-computed sigmoid values and retrieves the appropriate value based on the input. Here we have clock X and the input with parameter, which is the in with. X is nothing but the input data. The memory array mem is defined as a two-dimensional array 2 to the power of in with entries, each storing a sigmoid function value of with data with. Initialization. During initialization, the initial block, the module reads the sigmoid function values from a memory instantiation file sigcontent.mif and stores them into the memory array. During each positive edge of the clock, the module transforms the input data X into the format suitable for indexing the memory array. If the input value is non-negative, the module adds a bias to the input value X to obtain the index Y. The module retrieves the sigmoid function value corresponding to the transformed input Y to the memory array and assigns it to the output port. Now, let me pass it on to my teammate Raghav.
So this is the Zynet file. It is a Verilog code which represents a hardware design for a neural network inference accelerator using AXI protocol, which will be used for communication between different modules. So you can see the parameters of AXI data width and AXI address width, which basically shows the data width and address width of the interface to be used. You can also see the basic inputs of clock reset and input data validity, etc. So uh, and the outputs include AXI in data ready and interrupt. So here down you can see the AXI light wrapper instantiation. In this, the wrapper module acts as an interface between the AXI light interface and the internal logic of the accelerator. It maps AXI light signals to the corresponding internal signals used by the accelerator. The state management, if you are to talk about the state management and data pipeline, so the each layer of the neural network processes the data sequentially and uses pipelining to maximize its throughput. For here you can see that each layer corresponds to the submodule. Yeah, so for each layer there is a corresponding submodule. Like here it is written as layer one. Down if you see there will be layer two and all. So the each submodule computes the output of its layer based on the input data received from the previous layer. The state machines, state one, state two, etc., control the flow of the data through each layer, including buffering and valid signal generation. In the signal propagation and synchronization, you can see that this O valid basically checks for the validity of the output, and the output of each layer, like which is the X out, is basically buffered in through the hold data 1, hold data 2, etc., and synchronized with the AXI interface. The Here you can see that AXI read data is basically assigned the output of the final layer for the read access of the from the AXI interface. In the reset handling, so in the reset handling, a reset signal is generated internally and synchronized with the AXI protocol to reset the entire accelerator. The accelerator continuously processes input data from AXI stream interface and produces output data. Once the output of the final layer is valid, an interrupt signal interrupt, which I showed you earlier, is inserted to notify the external. So this is the TOPSIM module. It acts as a test bench for the Zynet module, which is a neural network accelerator. So basically what happens is it configures weights and biases and sends the test data and evaluates the results. Test data is read from files processed by the neural network accelerator and compared against expected result. Test execution stops after processing all the test data samples. So in this Verilog code, AXI protocol is used to establish communication between TOPSIM test bench module and the Zynet neural network accelerator module. AXI provides a standardized interface for efficient data transfer and memory configuration. So about the data transfer, input data is sent from the test bench to Zynet module using AXI write transactions, while output data is retrieved from the accelerator using AXI read transactions. This enables seamless exchange of data between the test bench and accelerator during neural network processing.
Hello guys, so now we are going to be looking at the test bench for this code, test bench for the neural network, and the simulation of it for some X number of test cases. So we have named the test bench as TopSim, which basically instantiates the main neural network module, which also has the AXI light interface. It takes clock reset and all these inputs, and basically here there is a logic that opens a certain file that has the test data. As you can see, this is there in the same directory as our project. So if you open any random test data, it basically has the 784 pixel values in binary, and in the 785th line there is the actual digit. So if we now simulate this test bench, as you can see, Now, after the simulation, we can see that the test bench basically runs through the first 100 testing examples of the MNIST dataset and prints out the accuracy, detected number, and the expected number. As you can see, the test code basically prints out the accuracy right into 100 byte test data count. We can also see in the source where we have added the memory files for the base and the bias and the weights. Everything has been added in the form of .mif or memory instantiation files. So after all the testing examples have been run, we finally get the actual accuracy of all the 100 testing examples. Here we are getting about 95%. This thing can be tweaked by using this include.v file. Here basically we can configure the architecture of the neural network. We can configure the number of layers, number of neurons in each layer, the activation function in each layer, etc. So by tweaking this, we can get better accuracy if we wanted to. So that's pretty much it about the simulation. Now we'll be moving on to the FPGA implementation. Hello guys, so now we are going to be seeing the FPGA implementation of the neural network. So as you can see here, we have a basic whitest code that takes the inputs from a header file datavalues.h and feeds it into the neural network using an AXI protocol. So this datavalues.h is being generated using a custom Python script that takes the image path as an input and outputs the header file. So this is basically the image that we are using. The digit 7 is being written here, and the Python code outputs this header file, which we can copy paste into the Vitis code. So after doing that, we build the project. So we use a standard serial monitor like Teraterm, set at the baud rate being set at 115200 to capture the input from the processing system of the FPGA. So after it's being built, we run it as hardware. We launch it in the hardware. As you can see, it programs the FPGA and the blue light turns on. And we can see that the detected number is 7 and the expected number is 7. So this processing, the neural network processing, is being done in FPGA, and the final output is being presented in a serial monitor. Thank you.